Hello, I'm Fred. This is a joint work with Guy and Enric, and it's about prediction-centric learning of tree Ising models. And in this talk, about half of the talk, I'll be explaining what that means. What's this graphical models? What is this prediction-centric learning? Why is it so interesting to study prediction-centric learning? And why is it maybe the right metric to study? And the second part, we'll get into some more meaty technical details. Why are we proposing a new algorithm for learning tree Ising models? It's because Chow-Liu doesn't work for this metric. And the solution, I'll give some ideas. How do we fix the Chow-Liu algorithm for this problem? Okay, so let's start with the very basic. What is an undirected graphical model? Basically, it's like a whole field of study, but it centers on this thing called the Markov property. And the Markov property is a way of saying that even though I have this distribution over p variables, which in general could be a very complicated thing, if you have the Markov property with respect to a graph, you actually are not that complicated in some sense. And what it means is that if you look at this green variable xi, you look at its neighbors, the red variables. If you have the Markov property with respect to this graph, it means that xi is independent of all of the blue variables, conditional on the red variables. And like in a wide number of applications, this is really important because it lets you actually perform some kind of reasoning about the variables, just like in probability theory. If everything is independent, things are very easy. And so graphical models give like a whole framework for describing high dimensional distributions in sort of a simple way. And there's like a really concrete application that graphical models have been used in. There's this problem of like collaborative filtering and recommendation. And so you could think that there are a bunch of users and a bunch of items, and you're trying to understand which items users like. So for example, maybe they're shopping on Amazon or something, and you're thinking like, oh, what do they want to buy? And the hope, and how you do it in an application with the graphical model is you try to learn a graph which explains, liking one thing maybe correlate with liking another thing, and we try to find a graphical model which models all of those correlations. And so there's all these edges, and maybe an edge will have a plus label if, say, liking coffee is positively correlated with liking Justin Bieber, and it would have like a minus label if liking coffee is kind of negatively correlated with liking Justin Bieber, for example. And then the great thing is once you have a model like this, you could answer new questions like, what's the probability you're going to like Justin Bieber's album given your past purchases? And not only would you be able to predict that, but you'd be able to predict it in kind of an interpretable way. Like there would be a simple model that tells you, oh, because of these reasons, we think you'll like Justin Bieber. Okay? And so you would like I said, to learn that kind of model, by looking at a bunch of user data. And, to really be formal, we need to think more about what it means to learn. And this is the usual answer, which is a good answer in many cases, which is to learn a graphical model, the key thing is to learn the structure. And the structure is just the graph. And so this is a very prototypical graphical model, the Ising model. It's a lot like a Gaussian distribution, but for discrete random variables. And so you have p plus minus 1 valued random variables that are all correlated, and the Ising model is a joint distribution where the log likelihood is quadratic. And then the coefficients theta ij, you can think of if those are positive, they encode that those two variables are like to be positively correlated, and negative if they like to be opposite. Okay? And then what does it mean to learn is you get samples from such a model, but the parameters and the graph of the model are unknown. And your task, the structure learning problem, is to recover the original graph in a computationally efficient way and from as few samples as possible. Okay, so that is a good definition actually, because the graph is the most important thing about the graphical model, and lots of other tasks are much easier once you know the graph. But on the other hand, there are some weaknesses of this definition. Okay, so that's the task. And one of the big weaknesses of this definition is that it doesn't understand actually that sometimes two graphs are different, but not in a way that's really important. Okay, so here are two graphical models. The first one on the left, it expresses that x1 and x2 are like 99.99% likely to be equal, and x2 and x3 are 99.99% likely to be equal. So all of the three of those things are very likely to be equal, but it's not the same graphical model as the one on the right, where I swapped x2 and x3. Because like in the first graph, x3 has degree 1, in the second graph, x3 has degree 2. And so those are different graphical models, and in some cases we do care, maybe to learn the difference between these very similar graphical models, but in many cases we also don't care. And if you think about it from the sample complexity perspective, because those two models are so close, you're going to need like at least 10,000, actually more samples, if you're going to be able to structure learn, if you have to distinguish those two models. And so maybe we want a definition which doesn't sweat so much about the difference between things which are ultimately very similar. And this is related to the second problem, which is what happens if the data does not come from a ground truth model? Okay, so why would we want to do that? Because real data, we don't always exactly know how it's generated. Nevertheless, fitting a model is very useful. And it's represented, by this George Box quote, and all models are wrong, some are useful. And like the example George Box had was, if you think about PV equals nRT, that's a very useful equation, helps you understand what's happening with gases. On the other hand, the only truly accurate model of a gas is that there's a bunch of little particles or atoms or molecules that are all crashing into each other in a complicated way. On the other hand, which one is more useful probably is the ideal gas law. So in many cases, we want to fit a simple and fairly accurate model to explain the real data. And so it's not really true that the data is generated from a graphical model, or at least from the model we're fitting. And so maybe we would like to define a new learning task which sort of fixes these weaknesses. Now, if you try to do that, probably the first thing you would think of is learning in total variation. So try to learn a model which in some natural distance is close to the distribution of the real data. So again, we have the Ising model, same as before, but now maybe the data is generated, could be from an Ising model or even from a different distribution Q. And the promise is that Q, whatever it is, it's close in distance to some Ising model. And then if you have that guarantee, it's kind of an approximation algorithms problem. Like there exists some nice simple Ising model which more or less explains the data, and your task as a algorithm is with as few samples as possible and efficiently you want to find some Ising model which is indeed close to the true one. Okay, so that's a natural definition of a learning problem which gets rid of the weaknesses. That's the definition of the total variation, by the way. It's just the sum of the absolute values of the probabilities. And okay, it's a fundamental problem, and recently it was proved that actually we do know an algorithm that's optimal for this task in the usual minimax sense. Okay, so that's all really good. So we have an algorithm that solves that problem, and why are we giving this talk? Well, there are some weaknesses to the total variation definition too. And it has to do, well, a lot of it has to do with the thing that we're actually in high dimensions. And that means, okay, we have P. P is the number of variables, or like the number of dimensions. In many cases, P is big, like, how many items are there in the catalog that we're trying to recommend, like a lot of them. Nevertheless, in the usual structure learning setting, you can actually learn the graph with only like log P samples. So with a very mild dependence on the number of dimensions. Now, what happens if we look at the total variation distance, and I want to learn a model which is close in total variation distance? Can I do it with log P samples? The answer is no. Even if the true thing, the data is actually generated from a tree Ising model, so that's an Ising model where the graph is a tree, you're going to need like P log P samples. Okay, so P log P, that's exponentially larger than log P. So that means you need a lot of data, actually, if you want to learn to a meaningful total variation distance approximation. And so, in summary, total variation learning, it requires a lot of data. It's exponentially worse than the number in P, the number of variables. And it really reflects a bigger problem, which is that the TV distance is very strong. So it's very hard to be close in total variation distance in high dimensions. And so if we go back to the motivation, like we want to fit a misspecified model, it's not useful if like, our definition of close is so stringent that nothing is actually close in total variation distance. So we would actually like to fit things maybe in a weaker metric than total variation. Okay? And so one way to try to think about what should be the right metric is to think, in some of these applications, what would be the kind of quantities we care about. And so for a recommendation system, what would it mean that the graph is a good model for this data? Maybe it's that like this model does a very good job of predicting posterior probabilities. So conditioned on a few items which you bought, what's the probability you're going to buy the Justin Bieber album? So you want this posteriors to be close to the true ones. And the way you can define this formally in a nice, elegant way is you can look over all sets of variables of size at most k, and you can just look at the total variation distance of those subsets of variable, of that set of variables S, between the truths and the model you're fitting. Okay, and we'll call this a local total variation. And this was studied in several works. Okay, and it was shown in those works that if you have a good fit in this metric, then indeed the posteriors are close. Okay, and the key thing here is we're only looking at small sets of variables. If we look at all the variables, it's just total variation. Okay, and this actually defines a family of distances, right? Because for each set size k, you have a different distance. But fortunately, they're all equivalent for constant k. And so for the rest of the talk, just think about k is equal to 2. So if we can solve that problem, then for tree Ising models, we're actually going to get a guarantee for k equals 3, k equals 4, k equals 5. And it's because actually there's a version of Wick's theorem which says that the high order moments can be expressed in terms of the correlations. And this was observed in this work by Bresler and Karzent. And so finally, we've come to the actual problem. So it looks very similar to the total variation distance problem. And the one difference is that we're promised the model is close to a Ising model in total variation, local total variation, and we're trying to find something in local total variation. And of course, for this talk, we're going to focus on this really classical problem of learning trees with this new objective. Okay? By the way, why are we trying to study this with trees? I mean, one reason, of course, is that that's classical. Like Chow-Liu in the 1960s were studying learning tree models. So it's a really fundamental problem. But another reason is that although trees are not good models for everything, they are good models for some kinds of data. And a tree is really, really good in the sense that it's very easy to interpret the predictions from a tree. And also you can compute the answer to basically any question on a tree really quickly using the belief propagation algorithm. So if a tree is a good model, then we would want to be able to fit one, right? And once we fit it, it's very useful. And so a little more formally, we're considering for simplicity the case without external field. So this local total variation is just asking that you get all of the covariances correct. So the mu ij, that's the ground truth covariance, and mu tilde ij is my notation for the fit covariance. And you can kind of think like, if the true model, say, were a tree Ising model, then there are these distances, there are these correlations which come from those model, and we're asking to return a tree which technically doesn't have to be the same tree, but matches in all these covariances. Okay, and for this problem, even if the ground truth is not a tree, if we have a promise there's a nearby one, epsilon distance local TV guarantee, if there exists a model which is within epsilon local TV distance, then with log p over epsilon squared samples, we can learn such a tree Ising model. And this is optimal sample complexity, and our algorithm is computationally efficient, polynomial time. Okay? And finally, I want to come back to the very beginning of the talk. We were saying structured learning is a really good objective, but it has these weaknesses. Now, this is an objective which actually generalizes structured learning. So what does it mean? When structured learning is possible, so you can assume edge weights are not too strong or too weak, then structured learning is possible. And whenever you have those assumptions, local TV close actually does imply the correct structure is recovered. So if it's actually possible, basically, to recover the correct tree, then this algorithm automatically recovers the correct tree. On the other hand, it makes sense, this objective makes sense even if, there's a couple edges which you can't exactly figure out, which ones they are. Okay? Okay, so how do we do this? like I mentioned, there's this 1960s algorithm of Chow-Liu. What is this algorithm? It computes basically the empirical mutual information between all of the variables, and then it computes the maximum weight spanning tree over those estimated mutual informations. And it turns out, as Chow-Liu proved, that's the maximum likelihood solution to this problem. And so that's a very classic algorithm, but it turns out when you have this kind of misspecification, it doesn't work very well. And so what happens is that here are two graphs. I can promise to you for an arbitrarily small epsilon that the true model is close to an Ising model on the left graph within local TV distance epsilon. And nevertheless, Chow-Liu will output something on the right graph. So they're both paths, but in one path you alternate between x and y, and the other one you do all the x's and then all the y's. So Chow-Liu, you can actually trick it into returning the right graph, even though any Ising model on that graph is very far in local TV from the correct distribution. So that's saying basically Chow-Liu is not useful for learning in local TV. The construction is very simple. You basically, because it's greedy, you can sort of easily cook up examples where Chow-Liu is tricked to pick wrong edges. But I won't go too much into the details because of time. Okay, so we know Chow-Liu doesn't work. Nevertheless, it's actually very useful for us because we can show that actually it sort of recovers at a very high level the correct structure. And what does that mean is that if you look at the weak edges that Chow-Liu returns, those are actually high quality. So you can actually use those in your final fit. And the only problem is like when you remove those weak edges, you get these connected components. And the fit that Chow-Liu outputs in each connected component, the subtree there, is not generally a very good fit. And so to solve that, we come up with this new algorithm inspired by tree metric reconstruction, which refits within each connected component and gets like the fine details. Or maybe not the fine details, but the strong interactions of the graph correct. So it's like a 2-scale algorithm. So this algorithm, the second step, it's based off this huge literature on fitting tree metrics. So this is like a famous result in this literature that if you have a distance metric which is close in infinity norm to a tree metric, there's actually an approximation algorithm which can recover a nearby tree metric. So that's the result of Agrawala et al. It's based on a very nice connection to ultrametric. In ultrametrics, you can actually solve this problem exactly. I won't get too much into that. Okay, but anyways, the Ising model can actually be viewed as a tree metric. So what you do is you define this distance d between u and v. That's equal to the negative log correlation, and that's the Steele evolutionary distance. And so you might think you can kind of try to estimate that from data and then fit a tree metric, and maybe that solves the problem. It turns out it actually doesn't work. So why doesn't it work? Well, you try to write down the estimator of the Steele evolutionary distance, but it's actually a kind of poor estimator. So you just plug in the empirical correlations. But even if the distance is infinity, so the correlation is 0, on the empirical data, like the samples, it's very unlikely that the distance is going to be infinity. So the estimate is actually extremely not accurate for distant points. So that means in particular you cannot apply. The assumptions for this tree metric fitting algorithm are not satisfied. Another issue is that actually the output tree metric would have extra nodes that, like Steiner nodes in the metric sense, and we don't really want that because we want to output a very simple model. And if the ground truth doesn't have hidden variables, we don't want to introduce those. So yeah, it seems bad because there's all these issues. So it turns out you can solve all these problems. The first one, which seems really key, is actually the Chow-Liu step. So Chow-Liu, we show, is really good with the weak edges and just has trouble with the strong edges. So by doing the first step of our algorithm, we get rid of all of those weak edges, and those are large distances which would have caused problems for the tree reconstruction. Then it turns out you can come up with a better estimate for the remaining large distances by looking at shortest path distances. It requires a bunch of work. And finally, there's a trick. You can kind of actually just take a thing with Steiner nodes and delete them without screwing up the fit. So it's in the same spirit as some classical results, although the technique is totally different. Okay, and to summarize, we showed that in local TV, we can learn tree Ising models. Local TV is a really good metric for learning misspecified models of all kinds. And the big question, I think, is can we do this, or how do we do this for more complex models? Thanks for listening.